Hi all of you. Welcome to another lecture of nanoelectronics. This is me, Maria Joseph, Assistant Professor in Electronics and Communication Engineering Department of MBC CET Pyramid, leading this session. In this class, we are going to learn about three different topics. One is X-ray diffraction analysis, one is PL spectroscopy, and the another one is UV spectroscopy. First, we are going to see what is X-ray diffraction analysis. We have all heard about the word X-rays. Here, we are going to learn about X-ray diffraction analysis. This type of analysis is actually used for the structural characterization of nanostructure materials, which means it yields average information regarding the grain size, the micro distortion texture, lattice parameters, and so on. Now, a material in nanocrystalline form can have physical and chemical properties much different from these bulk materials. That is, I have already said in the previous classes that a material in a very small size in a nanocrystalline form can have physical and chemical properties different from when they are in their bulk form. This is the figure of an X-ray diffraction. We have already studied this earlier when we were studying about the Bragg's law and so on, or about when you have learned about constructive interference. You have seen this figure. These are the incident rays, and we have an angle 2 theta here, and then the diffracted rays. Now the space between this is d, and we have this as d sine theta. Understood? You should keep this. Here also you have 2d sine theta. Just keep this figure in your memory as we are moving forward. Principle of X-ray diffraction. X-ray diffraction is based on constructive interference of monochromatic X-rays and a crystalline sample. That is, this principle is based on constructive interference of monochromatic X-rays and a crystalline sample. These X-rays are basically generated by a cathode ray tube filtered to produce monochromatic radiation, collimated to concentrate, and it is directed towards the sample. The interaction of the incident rays with the sample produces constructive interference when the condition satisfies Bragg's law. We know what is Bragg's law. N lambda is equal to 2d sine theta. This law relates the wavelength of electromagnetic radiation to the diffraction angle and the lattice spacing in the crystalline sample. We know all this kind of things as we have learned all these principles earlier. Now, these diffracted X-rays are then detected, processed, and counted. By scanning the sample through the range of 2 theta angles, all the possible diffraction directions of the lattice should be attained. That is, X-ray diffraction is based on a constructive interference of the monochromatic X-rays and the sample. Now, X-ray power diffraction, how does it work? It consists of an X-ray tube, a sample holder, and an X-ray detector. X-rays are generated in a cathode ray tube by heating a filament to produce electrons and accelerating these electrons towards the target by applying a voltage and bombarding the target material with the electrons. As we know, the electrons generated are accelerated towards the target material. When the electrons have sufficient energy to dislodge inner shell of electrons of the target material, characteristic thick X-ray spectra are produced. When the energy is sufficient to dislodge the inertial electrons of the target material, the X-ray spectra is produced. These spectra consist of several components, most common being K alpha and K beta. The specific wavelengths are characteristic of the target material. That is, there are different wavelengths for different target materials. That is, each wavelength will be a characteristic of a target material. Filtering by foils or crystal monochrometers is required to produce monochromatic X-rays needed for the diffraction. Now, copper is the most common target material for this kind of diffraction. Then what happens? These X-rays are collimated and directed onto the sample. As the sample and detector are rotated, intensity of the reflected X-rays is recorded. The X-rays are directed into the sample. As the sample and detector are rotated, intensity of the reflected X-rays is recorded. When the geometry of the incident X-rays impinging the sample satisfies the Bragg equation, we get the constructive interference and a peak in the intensity occurs. Detector records and processes this X-ray signal and converts the signal to a count rate, which is then output to a device such as a printer or a computer monitor. That is, it records the maximum peak where the intensity is maximum, and it records, and we can print it and see the pattern. This here, you just look through the figure, you can see that at some point the intensities are maximum, and here you can see the intensity is maximum. This is actually a recorded figure. Now, how does it work? The geometry of X-ray diffractometer is such that the sample rotates in the path of collimated X-ray beam at an angle theta, where the X-ray detector is mounted on an arm to collect the diffracted X-rays and rotates at an angle of 2 theta. Understood? That is, you have to look at the figure and understand that particular sentence. Just go through the first figure in this lecture and see it. For the typical powder patterns, data is collected at 2 theta from 5 to 70 degrees, the angles that are preset in the X-ray scan. Now we are going to the next topic, that is UV spectroscopy. The ultraviolet spectroscopy or ultraviolet visible spectrophotometry refers to the absorption spectroscopy or reflectance spectroscopy in the part of ultraviolet and full adjacent visible spectral regions. This means it uses light in the visible and adjacent nearby ranges for the purpose of identifying the materials. The absorption or reflectance in the visible range directly affects the perceived color of the chemicals involved. The absorption or the reflected the reflected wave in the visible range directly affects the color of the chemicals involved. In this region of electromagnetic spectrum, atoms and molecules undergo electronic transitions. Absorption spectroscopy is complementary to fluorescence spectroscopy in that fluorescence deals with the transitions from the excited state to the ground state, while the absorption measures transitions from the ground state to the excited state. That is, absorption spectroscopy or this type of spectroscopy is complementary to fluorescence spectroscopy. That is, it deals with the transitions from the excited state to the ground state, while absorption measures from transitions from ground state to excited state. About the fluorescence spectroscopy we are going to learn in the next topic. There the transition is from the excited state to the ground state, while here it is from in the absorption spectroscopy or UV spectroscopy, we have the excitation from ground state to the excited state. Then principle of UV absorption. Molecules containing bonding and non-bonding electrons can absorb energy in the form of ultraviolet or visible light to excite these electrons to higher antibonding molecular orbitals. That is, the molecules containing bonding or non-bonding electrons can absorb energy in form of the ultraviolet or visible light to excite these electrons. The more excited electrons, the longer the wavelength of the light it can absorb. The more easily excited the electrons, then longer the wavelength of light that it can absorb. There are 4 possible transitions and they are ordered as follows, like sigma, sigma star, n orbital or n to sigma star, pi, pi star and n to pi star. That is the possible transitions. Coming on to the PL spectroscopy, we have photoluminescence spectroscopy. It is a contactless, versatile, non-destructive, powerful optical method of probing electronic structure of materials. Light is directed into the sample where it is absorbed and imparts excess energy into a material in a process of photo excitation. In UV spectroscopy, we saw that the transition is from we saw it here. The transition it is from ground state to the excited state, but in the other case it is from the excited state to the ground state. Understood? That is the difference between the PL spectroscopy and UV. One way this excess energy can be dissipated by the sample is through the emission of light or luminescence. That is, it radiates the energy to the ground state and releases the energy. In the case of photoexcitation, this luminescence is called photoluminescence. Thus, photoluminescence is the spontaneous emission of light from a material under optical excitation. This light can be collected and analyzed spectrally, spatially, and also temporally. The intensity and spectral content of this photoluminescence is a direct measure of various important material properties. This is the figure that is showing, because it is it is to the down, or it is radiated to the ground. That is, the energy, losing of energy is more significant here. Now, these are my references. Thank you for the patient listening. Hope you will understand.